Hi everyone, welcome to day 18. You can put that in your planners for tonight. Here are your homework answers. And we'll pause here for 3 minutes to let you check the answers. And then I'll move ahead to each of the worked out solutions, which the sub can pause at in case you need to check the worked out solutions. All right, so I'll go to each of the worked out solutions on each of the page. Just shout out to the sub if you need it paused to be able to see the worked out solutions for those answers. So today's topic is we're going to estimate areas with trapezoids. This is in your white notes packet. Should say 2-18, and it's probably some of the last pages in that packet. And this is likely the first page there. We'll need calculators for at least one problem today as well, so you can be taking those out. So we have the fundamental theorem of calculus, which allows us to find the exact area under a curve. Well, why might we need the trapezoid rule to approximate areas when we've got an exact way? Well, we still could run into some problems. Say we have an integral like the example there. That's not something we have an antiderivative rule for. If we tried to do u substitution, du would equal 2x dx, and there's no 2x anywhere in the problem, so the u substitution wouldn't work. So we still have integrals that the best that we can do is to approximate them. Or what if the area is not a function? What if it's like an actual object, like the area of something that's not nice, say like New York State? Or the third thing, and this is the most common way that it shows up on the AP exam, is if you are trying to find the area under a function from a table of values as opposed to an equation. And we'll see a problem that is similar to how that's given on the AP at the end of this video. So the methods we've seen so far, we've had our Riemann sums where we do our left-hand endpoints. That's in the orange there. Our right-hand endpoint method, where each height is determined by the height at the right edge of the interval, and then the midpoint method. Those are the three we've seen so far. So the one new one that we're going to learn today is the trapezoid method. So the trapezoid method, think of it as like their trapezoids turned on their sides, where the height of the trapezoid is really this here, our delta x. And then we've got our base 1 and base 2 is the y values at either edge of the interval. Well, why might trapezoids be better than rectangles? Well, that slanted part of the trapezoid can better approximate the curvature of functions and give you a better approximation of the area. So actually sticking right on, or going over to, actually let's stay on that slide with the pictures here, and we're going to talk you through the setup for it. So in this picture here, let's label the A as our x0. Then this reference point would be x1, x2, x3, x4, and x5. So something to keep in mind is that the area of a trapezoid is 1/2 the height times base 1 plus base 2. That height is really our delta x because these trapezoids are on their sides, and the y values of each edge of the interval is the base 1 and base 2. So let's write out what our area of our region would look like. We would have, keep in mind each of these is delta x. So we would have a 1/2 delta x times, in parentheses, our base 1 and base 2 would be f of x0 plus f of x1. And that would be our area of the first trapezoid. Well, now our next one, we'll do plus 1/2 delta x for our height again because the trapezoid's tipped on its side. And now for our base 1 and base 2, in that second trapezoid, as we go left to right, we'll have f of x1 plus f of x2. And we're going to keep going like that. We'll have 1/2 delta x. Then we're going to have f of x2 plus f of x3. That's our third trapezoid. We'll keep going, plus 1/2 delta x. F of x3 plus f of x4 plus 1/2 delta x. F of x4 plus f of x5. And that's 5 trapezoids, and that's what we had. Well, let's see if we can neaten this up some. Notice everything has a 1/2 and a delta x. So we can pull those out front. So those are all taken care of. So all that would be left to add inside is all our bases, essentially, our f of our x values. Well, I want you to gaze at each of those for a second and notice if there's any like terms. The f of x0, that's the only one of them. But the f of x1s, we have 2 of them. And that's because that y value is used in both the first trapezoid and the second. The f of x2s, we have 2 of them. The f of x3s, we have 2 of them. The f of x4s, we have 2 of them. Oops, I forgot my 2 in front. But then we only have one f of x5 because that was only used in the fifth trapezoid. So all those middle ones have 2's in front again because those y values were used in 2 separate trapezoids, but the outer ones were only used in 1 trapezoid. And this is our basic setup for the trapezoid rule. The 1/2 is coming from the trapezoid formula. The delta x is our height. And then all of the interior ones get multiplied by 2. The outside ones only are used in 1 of them. Now, if by chance the delta x wasn't the same for each of the trapezoids, and that would really only occur in a problem that was given to you from a table, then we would just do the trapezoid areas separately and add them up. And that sometimes happens. But if it's a consistent delta x, then we could do it like this. All right, so let's see if we can estimate the area of square root of x plus 2 from 2 to 7, and we're going to do it with 10 partitions, or in other words, 10 trapezoids. So our width of each partition, we're going to do our b minus a, our 7 minus 2 over our number of partitions, 10. So this will give us 5/10, or in other words, a half. So we're going to have 1/2 because of the 1/2 in the trapezoid formula. And then we've got to do our delta x, which also happens to be a half in this case. And then we're going to have f of 2, our starting value. And then we're going to have 2's in front of each of the middle ones. So we're going to have 2 times f of 2.5 plus 2 f of 3 plus 2 f of 3.5, 2 f of 4, 2 f of 4.5, plus 2 f of 5, plus 2 f of 5.5, 2 f of 6, plus 2 f of 6.5. And then the last one, f of 7, remember that doesn't get the 2 in front because that was only used in one trapezoid. So this would be a pain to have to do in the calculator all the way. So what we could do is we could do 1/2 times 1/2, and you could put that in as a fourth if you wanted. We're going to do f of 2 plus f of 7. But then all the ones that have a 2 in front, we can do with a sum sequence. So we'll put the 2 out in front. We'll have sum sequence. We got to tell our equation that we were working with, which was the square root of x plus 2. Our independent variable, which was x. We have to tell our reference number we're starting with, or in other words, the first one that's plugged in. Now, because we're only doing the ones with 2's in front, our first one is 2.5. The last one would be the 6.5. And we got to tell what the step was each time, which was 0.5. Now, for these f of 2 and f of 7's, you can put it in an f1 if you wanted, or it's just square root of x plus 2. So this is just going to be 1/4. Square root of 2 plus 2 is square root of 4, which is just 2. Square root of 7 plus 2 is square root of 9, which is just 3. And then you can see what you get for your sum sequence. So what we're going to do is we're going to pause for 2 minutes to give you a chance to put this in the calculator. If it doesn't come out nice, do our AP rounding standard of 3 decimal places. So after you did this with the sum sequence, we should have ended up getting 12.665 for our area under the curve. Now, it may go on to the next page in your packet, but a follow-up question for this is our approximation an underestimate or an overestimate? Well, let's draw an example of one of our rectangles, or sorry, not rectangles, but trapezoids. And it can be tough to see there because it's not growing by that much. But imagine I drew it as an increasing function. That was a little more drastic. And I just made it a little steeper just so it's easier to see. But if you've got a trapezoid rule and our concavity, we're concave down, notice that slant should be underneath the graph. So because it's underneath, this should be an underestimate. So we've got an underestimate since it is concave down. All right, here's our next example. We're going to do 6 partitions, do it with trapezoids. And this one we're going to try and do without the calculator. So if we start out our b minus a over n, we'll have 4 minus -2 all over 6. So that's 6 over 6, which is 1. So we're going to have 1/2, because that's in the area of the trapezoid, times our height, which is the delta x1. And we're going to start out, we'll have f of -2. Then we'll have +2 times f of, our step is by ones. So we'll have -1 plus 2 f of 0 plus 2 f of 1 plus 2 f of 2 plus 2 f of 3. And then our last one we've got is just f of 4. So what I'd like you to do, the reason we're going to do this without a calculator is the function's pretty basic, x squared plus 2. So I'd like you to sub each of those into x squared plus 2, multiply it all out, and see what you get. So we're going to pause for 3 minutes to give you a chance to do that. All right, so here is each of your values subbed in. You've got each of your y values, and I left them with the 2 not multiplied out at first, just so you can, if you needed to check somewhere. And everything combined should eventually give us 37. So that represents our approximate area under the curve. And we have a follow-up question for this one also, wanting to know if it's underestimate or overestimate. Well, for example, here's at 0. I'm just going to draw a random trapezoid. I know it's too big. But here's a random trapezoid for our graph. Notice it's more area. So it's going to be an overestimate. And the reason is because this is concave up now. So we would have an overestimate since concave up. All right, one last one for today. We'll give you a moment to read through this problem. So this combines 2 topics that we have. One of them is average value of a function, which is the first thing we looked at after our first test in the unit. And then also using trapezoid rule. So let's just review quick, which is good review for the test also, average value of a function. So when you do average value of a function, we did 1 over b minus a integral from a to b of just our function. So in our case here, we're going to have 1 over 17 minus 2. We're going to want to do the integral from 2 to 17 of capital T of little t dt. So that 1 over 17 minus 2, that's going to be 1 over 15. And then this part, we're going to approximate with the trapezoid rule. So again, the 1 over 15 is because of the average part. So now our trapezoid rule will have the half because of the 1/2 in our trapezoid formula. Then we're going to need our delta x. Now notice our step in the table each time is 3. If it is consistent like that, we can pull the delta x out like we did in the other problems. If the step is not consistent, we would have to do the trapezoid area separately and calculate them each out. But we can pull that 3 out front, the delta x. So our trapezoids, that's 1, 2, 3, 4, and 5. That's going to give us our 5 trapezoids. So just like before, our first y value is just going to have 1 of them. Our interior ones are all going to have 2. So we'll have 2 times 40 plus 2 times 45 plus 2 times 52 plus 2 times 58. And then just plus 60 once. Well, a 15th times a half is 1/30th, times 3 is 3/30ths, which reduces to 1/10. So that'll make that pretty manageable to do without a calculator. So we'll have 42, we'll have 80, we'll have 90, we'll have 104, we'll have 116, and then 60. And we'll give you a moment to see if you can do this without your calculator. So when I do these in my head, I saw this as 220, tacked on the 80 to get 300. Those ones together were 102, so I brought these together to get 402. And then I still had the 90 to go, so you had 492 times 1/10, which would give us 49.2 degrees Fahrenheit as our average temperature. So again, that combined two different topics from this unit: average value, doing our 1 over b minus a in front of the integral of function, and then because it was from a table, the best we could do is approximate it with trapezoid formula. All right, that's it for this video. Any time left in the period, you can work on your homework. After homework, you could then be working, you want to be doing some of your review sheet tonight as well, and come in with questions to the for the next class. Have a great rest of your day.